In this lesson, we'll take a look at finding the volume of a solid of revolution using the cylindrical shells method. This is different than the washers or disks method, and it requires a different formula. So to start, here's an example of what it would look like. We have the function y equals 3x minus x squared. We are revolving it around the line x equals -1, and we produce this figure. So it looks similar to the shapes that we would get with a washer or disk. We just are using a different method to find the area here, or the volume here. So why are we using a different method? Why not just stick to the uh, shells or the washers and disks? Why move on to shells? Well, if we look at this, we will see that the function is in terms of x, but we are rotating it around essentially the y-axis. This is shifted. Don't know why they picked a more difficult example for the first one, but we would essentially be rotating it around like a y-axis or an x equals line. So when that happens, we can't use the disks because the letter of integration versus the axis of revolution aren't going to match up. So in the previous section, when we did the revolution, we had the same letter that we were rotating it on. So it was a function of x and we're rotating it over the x-axis. So that worked out using disks or washers. We had the same letter. So today we're going to have different letters. Again, this is not a great first example, so we'll go down to one that is a better example. We have this example here. So we have the function y equals the square root of x, and we are rotating it over the y-axis. So we have different letters. It's a function of x. We are rotating it over the y-axis. So this is when you're going to use shells, when you have different letters. Can you do washers and disks? Sure. You have to rearrange the function, though, to be able to use that method. So if you only want to use washers and disks, you can always do that. You just have to have your letters correct, or if you like shells and you always want to do shells, you can do that. You just have to have your letters matching up the correct way. It's best to use whatever the problem dictates. So if they give you y as a function of x and they ask you to rotate it over the x-axis, that's when you want to use the disks or washers. If they give you something like this, where it's a function y is a function of x, and they ask you to rotate it over the y-axis, different letters, you want to use shells. So what the shells look like? It's a lot more difficult to picture the shells versus the washers or discs. Washers or discs, you just stack a bunch of circles on each other and then you get your shape. For these, it's very hard to draw. They do have a little picture here of these different cylinders. So you'll notice this outside cylinder here, and then we have another inside cylinder here. So basically what we're doing is we're taking concentric cylinders and putting them together. Each of them has a thickness that's very, very small. You can think of it kind of like a nesting doll where there's a different one inside. We have all of these different cylinders inside, and the heights of the cylinders match up with the height of the function. That's basically what we're looking at. Again, it's very hard to draw. I'm not going to try to draw it here, but if you're still kind of unsure of what it would look like, you can just Google a image of the shells. So just Google, volume cylindrical shells integral. Put enough words in there, it'll spit you out what you're looking for. So there's a lot of good computer generated pictures that, again, I'm not going to try to draw. So here's another example of that first image they showed us, and I've drawn a little bit on it. That orange interior cylinder, and then I've got kind of a red one that would be a little bit wider, a little bit taller around it, and you can kind of see that would go on with the next one being here and around. So that's about the best I can do. Okay, so let's get to the actual math. How do we calculate these? Well, we need to use a different formula than we did for washers or disks. So for the shell formula, it is going to be 2 pi RH. We have the integral still from a to b. That's going to be determined from your limits if they give those to you explicitly, or for the example like we saw up here, it would be sort of a natural limit where that function hits the axis. So those are your limits. It's always going to be 2 pi, just like the washers and disks. If you want to move that 2 pi to the outside, you can always do that. If you want to leave it inside, if you're more comfortable, wherever you want it to go. For the shell radius is always going to be the function. So we're using this method because we have the function that's in the different letter than what we're rotating it on. So we always want to use exactly that function. We don't want to change anything about it. So the shell radius is always the function. The shell height is always the letter you're integrating. So for our equations, if it's 3x minus x squared, the height will always be x. It's whatever letter you're integrating. The shell height is always that letter. And that seems to confuse a lot of people on the first time going through this. Uh, it's always just whatever letter you're working with. So that's the only way that I can explain it. Make it easier on yourself. Always just use whatever letter you're integrating, and that's the shell height. Don't try to get fancy with it. It's always the letter you're integrating. Okay, so let's go through this example here. So we have the function y equals the square root of x, and we're rotating over the y-axis. You could rearrange this to be x equals y squared and then do the washers and disks method, and you should get the same answer. So we will do that. We'll do the new cylindrical shells method first, and then we'll go back to washers or disks and see if we get the same answer. Okay, so the limits of integration always come from the letter that you're integrating. So we are integrating x, so our limits of integration should come from the x-axis. So we have from 0 to 4 on the x-axis. So those are our limits. So we'll set up our integral from 0 to 4. 2 pi, it's always 2 pi. The radius is always the function. So our function is the square root of x. And the height is always the letter we're integrating, so just x dx. That should give us the volume of this solid of revolution. So we'll go over here to the calculator. We'll do from 0 to 4. 2 pi, make sure you put a multiplication sign there. Sometimes it's okay without it. Other times it yells at us. Close that one up. And then we'll type another parenthesis for x dx. And we get 128 pi over 5. Okay, so we've done that, and we got the volume here, and now we're going to verify that it's the same as the washers or disks method. So in order to do the washers and disks method, we need to rearrange the equation to be in the same letter that we're rotating it on. So if we're rotating over the y-axis, to use the washers, we need to make this equation x equals y squared. So we have x equals y squared. We're going to be integrating that now from the y limits, which are 0 to 2. So it'll be the integral from 0 to 2. That equation was pi r squared. So we'll do pi. The radius is y squared, squared. And it'll be dy. All right, so we should get the same 128 pi over 5. And that's going to be y to the 4th dy. All right, I figured out what I did wrong. I forgot to use the washers. I was just doing one disk, and that doesn't work for this. So shells is the correct method to use here. It is a lot easier than trying to rearrange this for washers, but I will finish this out here and show you the washers. Okay, so if we go back down to this, the outer radius is 4, and the inner radius is the function. So it'd be really 0 to 2 pi outer radius 4 squared minus the inner radius y squared dy. And that should produce the correct answer now. Pi out front. And it's just going to be y to the 4th. 128 pi over 5. Okay, so yeah, that kind of illustrates the principle. If you are presented the problem one way, probably a good idea to use the different version of the formula for that specific problem and not try to rearrange it to be something else. it's going to get more difficult if you try to do it in a way that they're not intending you. Can you still do it? Yes, but you have a higher chance of getting it wrong if you try to rearrange the equation, just like I did. Okay, so let's move on to another example here. We have this, it's the same function, and now they are rotating it around the x-axis, but they have given us the function in terms of y squared. We actually did this problem when we did the disks and washers method, so we already know the answer to this. So it was in the previous video. So if you remember that, awesome. If not, we'll go through it again and reproduce that same answer. So for this problem here, this one I would definitely suggest rearranging. We'll do it as presented, but I would definitely suggest rearranging this one because it is a little bit more challenging to do this. As we can see, the shell height here is not a standard part of the equation because the height is changing. So what we would have to do is the integral from 0 to 2. We are integrating with respect to y. I'll move 2 pi out front. The radius is always the function. They've kind of did it backwards from what I've been saying. They call their height what's changing, and the radius is just the letter. I always say the height is the letter and the radius is the function. It really doesn't matter. It's the same thing either way. As long as one of the variables, one of the quantities you're putting in is always whatever letter you're integrating, and the other one comes from the function, you're good to go. So don't worry about the difference in words. Same thing. So the function is y squared, but the shell height is 4 minus y squared. So the shell height here is 0 and the shell height here is 4. So it's changing, but it's not changing exactly as the function changes. So we have to take into account this extra little bit here. So again, this is not the best way to integrate this one. It is a little bit more challenging to do it this way. So I would rearrange this one. The height is 4 minus y squared. The letter of integration is y, dy. So I believe this should produce us an answer of 8 pi if I remember correctly. Hopefully I remember correctly. So 0 to 2, I'm going to put 2 pi out front. Oops. 2 pi, and we have the radius is 4 minus y squared, y dy. Okay, and we get 8 pi. Awesome. So we have this version of doing it. If we go back to the disks method, it's a lot easier. So what we would do is rearrange that equation again to be the square root of x, so y equals square root of x. And now we're rotating that over the x-axis, so we have the same letters we use the disks. So we have the integral, take our limits from the x, so 0 to 4, pi, the radius is square root of x, squared dx. So that it's a little bit easier for the setup. We do have to rearrange it. So again, there's a chance that we could get it wrong. Rearranging it, pretty easy equation. So we should be okay. We have pi times the square root of x. I know it's just x, but I'm going to go through all of it. Square root of x squared dx. Boom, 8 pi. So we get 8 pi both ways. The volume should be the same no matter which way we do it. The volume's not changing, just the method of finding it is changing. So we have the different method now if they are presenting you with a function and it's something like this, x equals y squared, and they're asking you to rotate it around the x-axis. This would be a time where you would want to rearrange, go back to disks. If they give this as y equals or x equals y squared and they ask you to rotate it on the y-axis, that is when I would keep it as this y squared and then rotate it over the y-axis. You are going to have a little bit of difficulty there. So rearranging the function as y equals x or square root of x, that would be helpful, and then go to the shells method. So it just depends on what you have in the problem, and it should give you the same answer. So you can always try it both ways and see if your answers agree, or you can just stick to kind of what's given and go through it that. So here's another example. We have the region bounded by the curve 4 minus y squared, so that is the upside down parabola part on the top here. And we have the line y equals x, which is the slanted line there, and x equals 0, and we are revolving it around the y-axis to form a solid. So it asks us to use cylindrical shells to find the volume. So it's nice when they ask us to do cylindrical shells, we know that that is the um, method to use. So this is a little bit different. It's got two functions now. So they do give us kind of the first step here, and then I'll cut you loose and see what you can do after that. But we have the two graphs, and the region that's going to be revolved, that's going to form this solid, is the space in between these two functions. So that goes back to the area between two curves, and you can see that they've got those subtracted. So the top function is 4 minus x squared, the bottom function is x, and we're subtracting that to find that distance, that area inside of there. So they are revolving that equation over the axis. So that is going to be your quote-unquote radius that you're going to put into the formula to get the volume. So take a moment, pause the video, and see if you can calculate the volume of this region. Okay, hopefully you've had a chance to calculate this. We'll take a look and see what we get. So we're going to do the integral. We are rotating it from 0 to 2. We're taking our numbers from the, that's not from 0 to 2. We're taking our numbers from the x-axis. So we do need to take a quick second here and realize, hey, that's not a 2. And to find that point, we can just use a solver on our calculator and figure out where these things intersect. So we have 4 minus x squared. If you didn't do this, your answer's probably off. Didn't mention it, so maybe you realized, maybe you didn't. We'll see what happens. Oops. Solve that for x. Okay, so we get these fun answers. So we're just going to use the approximate decimal for it, which would be 1.56. So we'll go from 0 to 1.56. So this is not going to be a nice exact answer. It's going to have some decimal in it. That's okay. So we have the 2 pi. I'm still going to put that out front. And then the radius is going to be the difference of functions. And the height is always the function we're working with, the letter we're working with, so x dx. So hopefully you got that set up. You might not have had that number on the top if you had like 2 or 1.5. Close, as long as you have the rest of it, you're in good shape. Okay, so let's go through and see what we get for this answer. Again, it's not going to be an exact answer. It should spit us back a decimal since we have a decimal limit. 0 to 1.56, and we have 4 minus x squared minus x times x. And we get 13.33. Okay, so there we go. We are given a decimal limit, so our decimal answer, it's not a pretty answer like the previous ones where it's fraction or whole number of pi. It's just a messy decimal, so good to go. Okay, so they give us a little bit of information about the summary of the shells method, so that's basically everything we've talked about today. They do talk about like horizontal and vertical and parallel, and we don't need to do all that. Just look at the letters that they give you. If they give you a function in x and they're asking you to rotate it around y, they're looking for the shells method. If they give you a function in x and they ask you to rotate around the x, use washers or discs. Easy as that. Don't have to worry about parallel, perpendicular, vertical, horizontal, any of that. So we'll go back up to this first example they showed us here and very quickly set this one up. So whenever we have an axis that is not the x or y axis, when our axis of rotation is shifted, we just need to include that in what we're integrating. And the way we do that is subtracting it. So we'll take the function and subtract it. It's always right minus left. So here our function is on the right of it. So we would be using 3x minus x squared minus negative 1. So when you have an axis of rotation that is not the x or y axis, you just subtract it off in the correct order. like you would be finding an area. So the right minus left, top minus bottom, whatever it might be. So if the axis of rotation was like 4, it would be 4 minus the function 3x minus x squared, since 4 is to the right of the function. The process from there is the exact same as we've been doing. So this would be our radius, our height would be x, and then our limits, same thing from the x-axis, and we would set it up with 2 pi out front. So that's the only difference. If you have an axis of rotation that is not the x or y axis, you just subtract the axis of rotation from the function you're working with. And they talk about it and they don't provide any answer there, but there we go. Okay, so that does it for these notes. Apologies that I was a little off on this problem with the forgetting that extra radius there. But again, that just illustrates that if they give you one method to do it, you should probably stick to that method. You can do either or, but it's best to use the given information the way they intended it. Sometimes they'll give us questions where they don't really, there's not a clear method to use. If they give us an equation like x equals y squared, something like that, you might have some leeway with that, but try to stick to what they give you. That way you're not making mistakes like I made there. And just be careful if they are intersections like this last example we did, that you calculate that point of intersection and don't just try to eyeball it from the graph and have a incorrect limit. But until next time.